Hi guys, Birdzell here. So let's talk about what is science and why you actually care. I know you've been learning about science for a very long time in your academic career, but my guess is you haven't learned a lot about what science actually looks like. So let's talk about that. So first, what is science? Define science. This is something you've been doing theoretically since, kindergarten. When most people think of science, they think of something that's crazy and wacky, the mad scientist blowing things up in a laboratory somewhere. The truth is, that's not really what science is about. The truth is, science is just about hard work, data collection, getting things wrong more often than you get things right, and trying to do better the next time. So whether you're out studying sharks in the ocean or you're working in a lab to discover something about DNA and everything in between, science is the systematic study of something that occurs naturally. So what is the actual goal of science? The goal is pretty simple, actually. It's to understand the natural world and universe. And when I mean universe, I mean anything in it. So this would apply to like astrophysics and things like that. Whether you're talking about studying something here that occurs on Earth near us, or whether you're talking about something like this, where this is actually a picture from the Hubble telescope, and each one of these little points is a galaxy. That's not a star. These are all galaxies. Galaxies, that word sounds weird. Galaxy. You live in the Milky Way galaxy and are right here. That's where you're at right now. That's where I'm at right now. That's where we are at right now. So if you imagine, science tries to understand things not only here in this little bitty tiny insignificant corner of this galaxy, let alone this entire universe. So anything that occurs in the universe is something that science will attempt to figure out. Okay, so who cares? Why do you care? This honestly is, I think, the most important thing for you to think about. Why do you care? First, to understand the world around you. Don't be anyone's fool. What does that have to do with each other? The better you understand the world, the universe, everything about it that you live in, the harder it is for someone to actually fool you. When you truly know what goes on around you and how it works and why and how science works, and when you learn to think critically about things and be a skeptic, it's really hard for anyone to fool you. Jobs, no matter what you do, it's going to relate to science in some way. Honest to goodness, everyday life. If science is understanding the world around you and you live in that world, then whatever you do in life, whatever job you have, whatever career, whatever life path you take, science will be involved in that. You can't look at your phone without seeing science right in your hand. Critical thinking and skepticism. We've talked about this a little bit, but I really, really want to emphasize it again. Really, don't be anyone's fool. The better critical thinker you are, the more you know how to use skepticism wisely, the harder it is for people to trick you or take advantage of you. And it makes a better place to live for us. It makes your life easier, right? That's what the technology part of STEM is. You take the science, you turn that into technology, and theoretically it hopefully makes your life easier. Whether it's a car to drive, a plane to fly in, medicine that actually helps you live a healthier, better, longer life, a phone that keeps you entertained, whatever it is, it makes your life easier. Okay, so that brings us to the actual two kinds of science. There's research science and applied science. Research science is usually what you think about when you think of a scientist in a lab doing work, collecting data. A scientist going out into the field, collecting data, writing papers. Applied science is taking that knowledge that the research scientists have figured out and applying it to everyday life. So those would be like doctors and engineers. They are applied scientists. They are scientists still in the fact that they're using science in their everyday lives and they have to keep up on what's going on it. But they're not actually doing the original research, so they're doing the applied part of that. Whereas the professors and the researchers and the institutions and the pharmaceutical companies and all the different industries that do research every day, those are research scientists. So this is another important question. What science can and cannot address. This is something that often gets confused, and once you understand truly what science can and cannot address, it can clear up a whole lot of misconceptions and a whole lot of conflicts for you. So, for example, can science address these things? Can it talk about the upside down, or the demons that might live there, or ghosts, or anything that's supernatural, higher powers? No. So when we get to science, the investigation of science actually, and we talk more about what a hypothesis is and how you test a hypothesis, one of the most important things for a hypothesis in your research is that it has to be testable. These things aren't testable, right? Like, how do you go test whether or not ghosts are real? As of right now, we can't. So science just doesn't even address that. How do you test whether or not some sort of higher power really exists? You can't, as far as science is concerned right now, or demons or anything of that nature. So it doesn't say that it's not real. It just says we can't test it. It's not science. That's another thing. That's another part of human endeavor. It's not science. So actually, what is science then? Again, it's anything that occurs naturally that you can actually see and observe and test and do something about. Now, that can be big, like the entire world. That can be big like the universe. It can be the stuff you usually think about, like I'm going to go out and I'm going to do some animal behavior studies in the jungle. Or it can be really, really small where you can't see it, but you can still test it, like in the case of molecules and chemicals, which you would do with chemistry. Those are things that you can actually have tests for, conduct research on, repeat, see if it's actually correct in the long run. That's science. Things that you can't develop a test for, that we have at this point no way to even tell one way or the other for science, with actual testable data. It's just not science. So it's not that it's not valid, it's just not science. This is another important thing to think about and get clear in your head when you're thinking about science and going forward. From here in this class, I want you to make sure you pay attention to these things. So these are important terms that are actually often misunderstood and misused. And when you understand how science uses these terms as opposed to how you might hear them in your everyday life, it will help you understand a lot more what science really does say and doesn't say. So let's start with proof. Actually, what is proof, right? Does it really exist? So for example, can you prove to me that the earth is really round? How do you know it's not flat? Like really, how do you know? Who has proven to you in any way that the earth is really round? Can you really do that? Is that possible? Well, I can fly up in a rocket ship and I can take a picture. Well, how do you know that's what they really did, right? That's the whole point behind like flat earthers or anyone else. Usually if we have this discussion in class, I will ask you to prove to me that you actually exist. And it turns out that's really pretty hard to do. No one's been able to do it yet. In all the years I've been teaching about this and having this discussion with students, no one yet has been able to prove definitively to me that they actually exist, and that you're not some figment of my imagination, we're not in some matrix, or who the heck knows, right? That's philosophy now. But the point is really, what is proof? Well, you think proof means that it's proven to be true, but what does that mean? For example, do I think the earth is flat? No. The earth is round. We have quote-unquote proven that is true. So what does that actually mean? That means, really, when we say proof, we're saying that it's a preponderance of evidence. We use it for shorthand for that. All the evidence, repeated over and over and over again, to the best of our abilities, have shown us that this is the same answer we get every single time. And we all kind of agree now that this is reality as close as we can understand to what reality is. It's hard to wrap our little human brains around this big thing that is the reality of the universe. But we can get close, we think, we believe. We have to, hold on to something. Therefore, we say all the evidence, the fact that we do believe that NASA has gone to space, turned around, take a picture of this. People have come back and said, I've actually seen from space, the earth is round. It's not flat. You can travel all the way around it without falling off, right? All these different things would show, math, all these things show us that the earth is round. The preponderance of evidence shows us that the earth is round. Okay. Natural. This is an interesting term, and there's multiple ways to use these terms, right? But in science, what does natural actually mean? So natural means it's can be demonstrated to exist in nature. Then it's natural, right? That doesn't necessarily mean it's good for you. And labeling of products and selling you stuff and whatever else, this is part of Don't Be Anyone's Fool. We're sort of led to believe that if it's natural, it's good for you, right? I'm here to tell you, just if it exists in nature, it's natural. That doesn't mean it's good for you, right? Take an atomic bomb. It exists in nature. We've created it, but we are natural. We exist in nature. Therefore, it's argued that, the atomic bomb is a natural thing. So in as much as something that is natural to the earth figured out how to make this atomic bomb. Or just radiation. Radiation naturally occurs all the time, everywhere. Doesn't mean it's good for you, right? Okay, natural chemicals that actually are good for you can be bad for you. Take, for example, water. There is such a thing as water intoxication. Water intoxication. You can poison yourself by drinking too much water. You can get the electrolytes in your body so out of whack by drinking too much water all at once that you can die from it. And it has happened every year. Someone drinks too much water in some sort of silly competition or for whatever reason, and they die from basically poisoning themselves with water. Does that mean water is bad for you? No, you absolutely have to have it. But it's all about how much, right? A little bit of radiation won't hurt you. A lot of radiation will hurt you. A little bit of water, not good. You need more than a little bit. A moderate amount of water, that's good for you. Too much water can be bad for you. So just because something is natural doesn't mean it's good for you. Organic is another one that has really taken over everyday commercial endeavor, I guess, at this point. You go into the store and, it's organic, so it's good for you and it's better and whatever else. Okay, so that's what it means like in the food industry. What it really means in nature is something entirely different. As a matter of fact, just because it's organic doesn't mean it's 100% awesome and no bad chemicals and everything's great, because those organic fruits and vegetables, they actually do have toxic chemicals in them. Cyanide in apples. Formaldehyde, the stuff you use to preserve specimens, in pears. Solanine in potatoes. That all exists. Those are all toxins. The thing is, they exist in such small amounts, naturally, that it won't hurt you. Your body can clear them, no big deal, deal with it. Just don't start, eating pounds of apple seeds, because you might die, especially if you crush them. So just because something is organic doesn't necessarily mean it's all chemical free. Literally everything is chemicals. You are a bag of chemicals. So what does it mean in science? It means that it exists in nature and contains the elements carbon primarily, and then usually or actually always hydrogen. There are carbon-hydrogen bonds in organic molecules. For example, this one, that is an organic molecule. It has lots of carbon, lots of hydrogen in it. That's what organic means. If you go on in science in college, you'll probably take organic chemistry, which, may the force be with you. No, I'm just kidding. Organic chemistry is tough, but it's good. It means you're going to study molecules that exist as a result of life in some way and have carbon and hydrogen in them. So next one, hypothesis. You've learned this. I know what this is an educated guess, right? No, this is not an educated guess. That's not what a hypothesis really is. So stop saying it's an educated guess. I'm educated. You're on your way to being educated. Not every guess you or I make is a hypothesis. That's not true. So what it actually is a claim or proposed explanation made based on limited evidence that serves as a starting point to keep investigating. You actually say, this will happen because, or this happens because, or if I do this, then this will happen because I know something, because I can figure something out from the knowledge I already have to answer a new question. That's what a hypothesis actually is. Important things about it. It must be testable, which means you have to be able to test it. You can't make a hypothesis that I think that the Demogorgon actually exists in the Upside Down, because you can't get to the Upside Down, and if you can, then tell someone, because that's kind of awesome and terrifying. But if you can't actually get there, so you can't actually test anything there. It has to be falsifiable. That means it has to be able to be proven false. For example, ghosts exist. Well, how do you prove that's not true, right? If you can't prove that it's not true, then you can't test it, really. because there's no way to say whether you're right or wrong. And if you can't say maybe I'm right and maybe I'm wrong, then it's not really a question of science. Hypotheses actually cannot be proven true. What they are is when you compare your results to your original hypotheses, it's either supported or not supported. Don't ever tell me the hypothesis was proven to be true. No, 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 no. No, that's not how science works. You can say we supported our hypothesis, we gave more evidence to lend towards this hypothesis. You can say it was not supported, so we no longer believe this how this works, or I no longer believe this is how this works. That's all valid, but you cannot say that you have proven your hypothesis true. I will mark you wrong for that every time. Okay, this is the big one. This is the really big one and the super important one. Theory. This is so misunderstood, especially when used in terms of science, and very, very misused in terms of science. This is one where how you hear it in every day is not what it means in science, and people think it is, and then they'll say, oh, a scientific theory, they'll mean this or that, and they're almost always wrong. So let's figure out here what a theory really means. If you have heard, it's just a theory, it's a guess, they don't know, it hasn't been proven, it's just an idea, they're not using it correctly when it comes to science. What it really is, and this is super important, it's well substantiated. I have to speak English. It's well substantiated. It's an explanation of some aspect of the natural world. It's based on a body of facts that have been repeatedly confirmed through lots of observation and experiment. They are not guesses. They are actually reliable accounts of how the world works. Theory is kind of like a big umbrella supported by lots of different facts and observations and laws underneath of it. So you can't necessarily turn a fact into a theory. Like, something doesn't become fact eventually if it's a theory, because theory is big, right? It's a broad explanation of how something works. It's considered to be generally true by science because it has been repeatedly tested in many different ways and shown to be true. So what does that mean exactly? You still think it's just a theory? Well, in case you didn't know, gravity is a theory, and I don't, or at least I hope, you're not jumping, off the tops of buildings hoping you will float, right? Gravity is a theory. Gravity is not a fact. Gravity is not a law. In science, gravity is a theory. So it's explaining a lot about physics is what gravity is doing. It's the theory of gravity. Okay, so if you are not willing to go to a cliff and jump off and say, it's just a theory, they don't even know if gravity's real or not, or whatever, I might not actually fall to the ground and break my neck. If you're not willing to do that, which I certainly hope you're not, then be very careful how you treat the word theory in science. Okay, so let's talk about some theories in biology that are often dismissed as just a theory, just a guess. Scientists don't really know. But now we know that if it's an accepted theory in science, a widely accepted theory, that it's well substantiated and we know it's fact, just like gravity. We can treat it like fact. So, one of these would be evolution. Hold on, before you panic. Yes, it's true. Evolution is a theory, but that doesn't mean we don't know it's true. We know that it's true, just as much as we know gravity is true. Now, do we know everything about how evolution works? No, but we'll get there. One of the big units we'll do this year is on evolution, and we'll talk specifically about what it is, what parts of evolution have been proven over and over again to the point where we accept it just as much as we do math theory and gravity theory and all kinds of other things in science, and what parts of the theory of evolution are still under investigation. It's a very complex umbrella of science, and parts of it we are very confident in, and parts of it we're still figuring out. The Big Bang. Well, what is the Big Bang? It's the start of the universe, right? Yes, we know something like that happened. We do know. We know a Big Bang happened, or is what we call it. What exactly that was, what exactly sparked it, we don't know. But we do know there was this big explosion that sort of started off the universe that we know right now, and it has been expanding ever since, and it has gone through this process of first being just largely hydrogen and some helium and atoms coming together and so on and so forth, and fast forward many billions of years and here we are. Okay, human caused global warming, climate change. This is not a theory. We know this is true, and we know that humans are largely responsible for it. Does climate change over long periods of time in the Earth, and has it in the past? Yes, it does. Has it ever been caused by humans before? No, we haven't really been around that long. So we got here and we caused the latest change in that. Is it bad or good? Well, I guess that depends on how you look at it. Personally, I think there's some concerns about it because it's happening fast and we're not keeping up with that. But we'll talk about that more later. But to say that it's not happening or that it's not caused by humans or largely by humans is just fooling yourself. It's a theory, but it's one that's very well substantiated at this point. Okay, so basically, if you've been paying attention, you should understand now that the ultimate goal of the science is to explain the natural world and the universe. That understanding science will hopefully help you be a better citizen and help you make better choices. That it will help you defend yourself against people trying to take advantage of you, because it'll make it really hard for others to trick you. And just as in life, everyday life, words matter in science. So understand how these words are used in science and use them correctly in science. And hopefully that gets us off to a really good start.